Today, we're diving deep into the cornerstone of system design, scalability. In a world where any app can go viral overnight, it's critical that our systems can handle sudden traffic surges without breaking a sweat. So how do we build applications that stay rock solid under pressure? Let's find out. First thing first, what exactly is scalability? At its core, a system is scalable if it can handle increased loads by adding resources without compromising performance. But there's another layer to this. Scalability isn't just about handling more work, it's about doing so efficiently. It's about applying a cost-effective strategy to extend a system's capability. This shifts our focus from merely surviving increased demand to optimizing how we scale. This raises some critical questions. If we add more processors or servers, how do we coordinate the work between them? Will the overhead of coordination eat into the performance gains we're aiming for? It's essential to consider these factors to ensure that adding resources actually delivers the benefits we expect. When we talk about scalability, it's more meaningful to compare systems rather than labeling them as simply scalable or not scalable. One effective way to do this is by analyzing response versus demand curves. Imagine a graph where the x-axis represents demand and the y-axis represents response time. A more scalable system will have a curve that rises less steeply as demand increases. This visual comparison helps us objectively assess the scalability of different systems. Now, it's important to acknowledge that no system is infinitely scalable. Every system has its limits, and eventually, demand will outstrip resource availability. This tipping point often appears as a knee in the response versus demand curve, where performance starts to degrade rapidly. Our goal in system design is to push this knee as far to the right as possible, delaying that performance drop-off for as long as we can. So, what typically causes scaling bottlenecks? There are two main culprits: centralized components and high latency operations. A centralized component, like a single database server handling all transactions, creates a hard upper limit on how many requests our system can handle simultaneously. High latency operations, such as time-consuming data processing tasks, can drag down the overall response time, no matter how many resources we throw at the problem. However, sometimes centralized components are necessary due to business or technical constraints. In such cases, we need to find ways to mitigate the impact, such as optimizing the performance, implementing caching strategies, or using replication to distribute the load. Alright, so how do we build systems that scale well? Let's focus on three key principles: statelessness, loose coupling, and asynchronous processing. First up, statelessness. This means that servers don't hold on to client-specific data between requests. By keeping servers stateless, we make it easy to scale horizontally because any server can handle any request. Plus, it enhances fault tolerance since there's no crucial state that could be lost if a server goes down. However, it's important to note that some applications require maintaining state, such as user sessions in web applications. In these cases, we can externalize the state to a distributed cache or database. This allows the web servers to remain stateless while the state is preserved. Next, loose coupling. This is all about designing system components that can operate independently, with minimal dependencies on each other. By using well-defined interfaces or APIs for communication, we can modify or replace individual components without causing ripple effects throughout the system. This modularity is important for scalability because it allows us to scale specific parts of the system based on their unique demands. For example, if one microservice becomes a bottleneck, we can scale out just that service without affecting the rest of the system. Lastly, asynchronous processing. Instead of having services call each other directly and wait for a response, which can create bottlenecks, we can use event-driven architecture. Services communicate by emitting and listening for events, allowing for non-blocking operations and more flexible interactions. This approach helps mitigate tight coupling and reduces the risk of cascading failures in complex systems. However, asynchronous processing can introduce complexity in error handling, debugging, and maintaining data consistency, so it's crucial to design these systems carefully. When it comes to scaling strategies, we have two main options: vertical scaling and horizontal scaling. Vertical scaling, or scaling up, involves increasing the capacity of a single machine. This could mean upgrading to a larger server with more CPU RAM, or storage. It's straightforward and can be effective for applications with specific requirements or when simplicity is a priority. For example, vertical scaling might be preferable for database systems that are challenging to distribute horizontally due to consistency constraints. However, vertical scaling has physical and economic limitations. We can only make a machine so powerful and costs can skyrocket as we approach the upper limits of hardware capabilities. Horizontal scaling, or scaling out, involves adding more machines to share the workload. Instead of one super powerful server, we have multiple servers working in parallel. This approach is particularly effective for cloud-native applications and offers better fault tolerance. It's often more cost-effective for large-scale systems, as we can add or remove resources based on current demand. However, horizontal scaling introduces challenges like data consistency, increased network overhead, and the complexity of managing distributed systems. Now, let's get into some concrete techniques for building scalable systems. First, load balancing. Think of load balancers as the traffic hub of a system, directing incoming requests to the servers best equipped to handle them. Without load balancing, we might have one server overwhelmed with requests, while others sit idle. Load balancers can use various algorithms like round-robin, least connections, or performance-based methods to distribute traffic efficiently. Next up, caching. Caching is like giving our system short-term memory boost. By storing frequently accessed data closer to where it's needed, whether that's on the client side, server side, or in a distributed cache, we can significantly reduce latency and decrease the load on our backend systems. Implementing a content delivery network can also offload traffic and improve response times for users globally. As our data grows, sharding becomes essential. Sharding involves splitting large datasets into smaller, more manageable pieces, each stored on different servers. This allows for parallel data processing and distributing workload across multiple machines. The key is to choose the right sharding strategy and keys based on the data access patterns to ensure even distribution and minimal cross-shard queries. Carefully selecting shard keys helps avoid hotspots where some shards become overloaded while others are underutilized. A golden rule in scalability: avoid centralized resources whenever possible. Centralized components become bottlenecks under heavy load. Instead, think distributed. If we need a queue, consider using multiple queues to spread the processing load. For long-running tasks, break them into smaller, independent tasks that can be processed in parallel. Design patterns like fan-out, pipes, and filters can help distribute workloads effectively across our system. Finally, embrace modularity in system design. By creating loosely coupled, independent modules that communicate through well-defined interfaces or APIs, we enhance both scalability and maintainability. This modular approach helps us avoid the pitfall of monolithic architectures, where changes in one area can have unintended consequences elsewhere. In a modular system, we can scale, modify, or replace individual components without impacting the entire application. Building a scalable system isn't a set-it-and-forget-it task. It's an ongoing process of monitoring, analyzing, and optimizing. Keep a close eye on key metrics like CPU usage, memory consumption, network bandwidth, response times, and throughput. These metrics are invaluable for identifying bottlenecks and making informed decisions about when and how to scale. As our applications grow and evolve, so too will our scalability requirements. We need to stay flexible and be prepared to adapt our architecture as needed. What works today might not be sufficient tomorrow. We should continually reassess our design decisions and be ready to implement new scalability techniques as our needs change. If you like our videos, you might like our system design newsletter as well. It covers topics and trends in large-scale system design, trusted by 1 million readers. Subscribe at blog.bytego.com.